Hello and welcome to my presentation on the physics of positron emission tomography, a medical imaging modality which you've probably not heard of so far. Here on the left you can see such a scan, which is, probably you've heard of CT and MRI, but PET is just a different story, let's say. It's way more into particle physics, and if you're interested in that, let me take you on a short journey. So a few words up front to me. So I did my Abitur in 2011. I focused on math and on physics, and then it was no surprise I ended up in physics. In 2014, I worked on radiation therapy. So here you can see like a typical planning, 7 points of radiation, and we basically simulated that using some other tools in particle physics. So that was what I worked on in my bachelor. In my master, I already focused on PET and basically on the detectors and measuring and simulating the light distribution in crystals, which was quite hard to do. And then in my PhD, I took it one step further. Now I am working on PET image reconstruction. So after we've detected the particles, generating an image from them. What we will talk about in this short presentation, this short video. First, I'll give you a wrap up about medical imaging modalities and why some are more interesting than others for me. Then we talk about PET itself, basic principles, and all the points where physics is involved in this. And then we talk about image reconstruction, which will be like my part, basically the most interesting part for me. But I tried to shrink it down for you to understand it. And then I'll give you some recommendations to watch next. So medical imaging modalities usually display the anatomy of a patient. So for example, if you do an X-ray, for example, at your dentist, or you do a CT, so this would be like a slice of a CT image, and you can nicely see the anatomy of the patient. You can see the lungs, you can see the spine, the hips, you can see the rib cage as well. And the same, so the CT has a nice contrast between bone and tissue, and MRI has a bit more tissue contrast, but basically it's also the anatomy of the patient. However, functional imaging itself, there is also fMRI, so functional MRI imaging, but we are going to focus on positron emission tomography. And for this scan here, there was also a PET scan performed. So you can see here, it's basically, you could also overlay it, but you can see here that some regions here have got a high or black spots, let's say, in regions where you can't see any difference from the CT. And this is because the PET scan shows the function of the tissue and not the anatomy. So this is basically tissue density, tissue attenuation, and this is something involved in the biological function of the tissue. It's also nice to combine those two. So for example, in here we got a CT scanner, and just behind there's a PET scanner. And if you open this up, it looks something like this. So there are lots of detectors around your patient. It's up here. And focus on CT first, because it is in a way similar, but then it is not. So first, CT, it has some basic principles, let's say. So in CT, what you do is usually you shoot electrons onto a target and they create Bremsstrahlung, so gamma particles. And those gamma particles, while these electrons here travel on this anode, these gamma particles go through your patient, and depending on how much current you apply here, they have more or less energy and can pass the patient better or less well. And then what you measure in your detector, you can differentiate this based on the absorption in the tissue. And if you do this from multiple angles around the patient, you can basically reconstruct a 4D image based on the anatomy. So you may ask, why are we interested in the function of the tissue? And there are two main applications. The first is oncology. A tumor will behave different than normal tissue. So, because it has a different metabolism. So, for example, here, the liver of this patient looks pretty homogeneous in the CT scan, but you can see that there are some regions that behave different. So these regions have a high uptake of this tracer, while this region here doesn't have this high uptake. So there's definitely a difference, and these regions here, this one and this one, might be tumors or metastasis. The other thing, let me just quickly erase those. The other big application is in neurology. So, for example, in here, the University of Pittsburgh injected a tracer into the patient, and they did PET scans of it. And this is an Alzheimer patient, and this is a control group. And you can see here the uptake is way higher in this brain than in the one on the right. And this is an indication for Alzheimer's. And this all sounds really novel and innovative, but it is an established method. There are like 140,000 PET scans performed in Germany each year. How does it work? Well, I'm going to tell you now. So, first of all, we inject radioactive material into the patient, which sounds crazy, I know, but those tracers are actually specific molecules which bind in the patient's body to specific tissues. So, for example, we have FDG, which is glucose, so sugar, and this is especially taken up by the brain and as well by tumors because they split, they need a lot of energy, so they have a high glucose uptake. And then there's also, for example, estrogen, so FES, and this would be especially useful in breast cancer, for example, because there, if you would want to see whether metastasis has also some receptors for estrogen or not, that could also influence your decision on the treatment. And the male equivalent would be prostate-specific membrane antigen, so PSMA. It's going to usually the tracer part, so the molecule itself is modified to be radioactive. And this radioactive molecule then distributes in your patient freely. And depending on the tracer, it binds to specific tissue or not. And on the right side, we can see now how such a distribution takes place. So it is injected into the vein, into the leg, and you can see it going through the lungs, through the heart, into the brain, all the arteries you can see. And you can see how this tracer distributes in all the organs. You can see the liver, you can see the heart, now you can see the kidneys because they're filtering it. And now you can see the bladder really well, right here. And you can also see the brain has got a really high activity because this is an FDG scan actually, and the brain is just using a lot of energy. And yeah, I think that's a really interesting video. And let's start with the basics. Radioactive decay. So what is it? You've probably heard of Becquerel and Marie Curie. So Marie Curie also giving the name for the grant that is called hybrid in my case. And there are a lot of Marie Curie actions sponsoring videos like this. So back to the topic of radioactive decay. So let's say we look at the nucleus and we have a certain number of protons and a certain number of neutrons in this nucleus. And depending on the number of those, they are stable or they are unstable. And if they are unstable, they may decay. So all of those orange nuclei, all of those isotopes, you can see here, decay by beta plus decay. So that means they decay emitting a positron. And this is, as you probably guessed, the basic for positron emission tomography. So what happens now? Let's look at some isotopes, the most commonly used. For example, 15 oxygen or 18 fluor, and the time it takes for such an isotope to decay. This would be like the first thing to focus on, because if you want to inject this into the patient and it takes some time for the body to take up, you need a specific time that your isotope is still there. You want to measure it in an equilibrium state, ideally. So, for example, in oxygen, this is mainly used in cardiology, actually. So if you inject this, you have to be incredibly fast, because after 2 minutes, you only have half the radiation left. So it is possible to use it, but for example, as I said, mostly in cardiology. And the most commonly used is 18F. So this has got like 2 hours half-life. So it can, for example, accumulate in your body for an hour. So mainly used with sugar as well. Accumulate in your body for an hour or something. And then you can see where tumors are. And then there's also some other isotopes with like a middle half-life. This was mainly used for PSMA, the prostate-specific one. And then there's also another property of those, not just the half-life, but also the energy at which positrons are emitted. And it's actually not that easy to say a positron has exactly that energy, because we'll come to that in the next slide, actually. But the maximum energy is kind of fixed. So as an example here, 18F, the range of those positrons is actually smaller than those of other isotopes which have a higher energy, which shoot those positrons out way faster. And this is what we're coming on. So if we have our 18F, it will decay into some stable oxygen, giving a positron, giving a neutrino, and some energy. How this energy is distributed among the 3 particles is not that easy to say, but as I said, the more energy they have, usually the longer they travel into the tissue. So if you have your decay and your positron is shot out, it will have some energy, and it travels through the tissue before annihilating with an electron. So at some point it will hit some electron. So it will bounce a few times, and this distance, as I said, depends on the energy. But in the end, it will hit some electron, and then it will, as you know, this is antimatter with matter, the exact opposite part. So an electron and a positron will decay into pure energy. And this pure energy will produce 2 gamma particles. So the process is called annihilation. And if you hit this electron, the 2 gamma particles coming out will fly into opposite direction. So this is conservation of momentum, basically. And those 2 gamma particles are the basic thing in the end we measure, the basic particle. So originating from the positron, 2 gamma particles are ejected, and those we can measure even outside of the body. So in comparison to CT, in CT we have a source going around the patient and shooting through the patient, and we measure something in a detector on the other side. If there's some bone involved, it won't come through. So our contrast is based on the attenuation of the patient. However, in PET we have certain positions where tracer is, where annihilations take place, and those annihilations go out randomly, but the 2 gamma particles are always going into opposite directions. So let's say we have those 4 annihilations and 8 gamma particles in the end. Then you can see, for example, in this case, we measure this particle here and this particle here. Sorry for that. But it can also happen that some particles are absorbed. And this is why it is usually a great idea to combine those two. So to have a way of knowing how much particles will basically come out of your scanner, because here you just measure one and you don't know where the other went. So, but here, in stark contrast to CT, the contrast here is based on the distribution of the tracer, and this attenuation is more like an annoyance. We don't want this to happen. Basically, if we could have all of the particles measured, we would be way happier. However, obviously that's not that easy, but the principal difference is in here we have a source outside of the patient going through the patient, and we measure the contrast. Here we have the distribution of the tracer inside the patient. The patient is our source of radioactivity. Okay, let's talk about the interactions of gamma particles. And as I said, the absorption is giving the contrast in the CT. Let's look at absorption. If a gamma particle interacts with or if it is in the region of interacting with an atom, it can happen that it doesn't interact. It just goes through or passes it. But it can also happen that there is absorption. So the gamma particle, here this red line, is coming in, hitting an electron in an inner shell. So this is a simplified atom model, hitting an electron, shooting it out of the, basically shooting it away from the nucleus, and then another electron can occupy its space and emit a low energy gamma. So in green displayed because it has such a lower, way lower energy than the gamma particle we put in, which is stopped. So our gamma particle is gone after that. We just got a really fast electron and a low energy gamma, but our original high energetic gamma particle is stopped. And obviously we don't want that in PET because then we can't measure the coincidences of the particles, the gamma particles we want to measure. We come to what coincidences are in a minute. However, another thing can happen, and this is Compton scattering. So a gamma particle coming in, interacting with an outer shell electron, and this electron flying away again. But it was so loosely bound that we just lose a bit of energy and our gamma particle is still carrying on. But it is slightly deviated from its original path. So we have like an angle here. And this is in general problematic because it changes the line we think is straight because of our photons being perpendicular or into opposite directions. So let's talk about that a bit. A true coincidence, as I said, an annihilation takes place, two gamma particles, opposite directions, two detectors are hit, one here, one here. This is how it should be. However, if we have scatter, two gamma particles can be ejected, they go into opposite directions, but one is having an interaction here, a Compton scattering interaction, slightly deviated, and it hits again this detector. And then what we think where the annihilation took place is not where it took place. So here our annihilation is here while it should be, we think it is here while it should be here. And there can be a third thing based on absorption in the patient, like displayed here, but it can also happen that basically you do not measure two particles from coincidences and measure two particles belonging to different annihilations taking place at the same time. So you think that those two particles you measured here belong to one annihilation around here, while actually there were two annihilations taking place at the same time. So those are some problems, basically based on the interactions of the gamma particles with matter. So why this is really interesting. So this basically is giving us contrast. This is what we want, and this is just what we absolutely do not. So usually if we do corrections, for example with the absorption, we can do that using the CT image. So if we have this coincidence and we measure it, that is good, but it is less problem than interaction here. If this would be the line of response, so the line between the two detectors, then here would be way less material and way less chance for the gamma particle to get stuck. But this is a correction you can do. And for example, if the annihilation would be here, it would be even more filtered, basically. And if we measure it, we have to be even more thoughtful of how hard it was for this coincidence to actually arrive at our detectors. The next thing, the random correction. As I said, if two coincidences happen at the same time, well, almost the same time. So we have like usually what we inject into a patient are 307 megabecquerel. So 370 million radioactive decays a second are happening. And if we measure two in a time window of just 2 nanoseconds, then we say this is a coincidence. Can still happen. I mean, 2 nanoseconds are extremely short, but there's a lot of activity. So it can happen. It's like it is in the data, and we can estimate it. It's pretty straightforward. But we have to do this. And then there's also the scatter correction. And this is the most complicated correction of those three. And there's actually a formula giving you the energy loss at a specific deflection. So if a particle is coming in like this, in this direction, actually as my camera is mirrored in this direction, then your particle, we have to look at this purple line here. This is for energy, 511 keV, which is the mass of an electron. The electron and the positron both at 511 keV mass, and after the annihilation, each of our gamma particles has an energy of 511 keV. So we can see that mostly, if there's an annihilation, it's rather straightforward, but it can also be slightly deviated. I won't go into detail in this regard, but it is like a common formula, and it has to be corrected. And let me take that away right now. We are already using simulation software to correct for this. And in one of the videos, we will also focus on whether we can reduce the amount of scattered coincidences based on the energy loss. However, in the end, energy loss, if there is energy loss, can we measure it? So if we measure the energy of our particles pretty precisely, we can reduce the amount of scattered gamma particles. And if we measure when exactly the gamma particle hit the detector, we can also reduce the amount of random coincidences. We can also use it for time of flight path. I won't go into detail on this, but it basically gives you more knowledge than just the line of response, as I said. So our detectors usually consist of a scintillator, and this is a high density, optical, basically looks like a piece of glass. But what it does, if it is hit by a gamma particle, it produces optical light, so low energy photons. And those low energy photons we can measure. So if a gamma particle with 511 keV hits those crystals, you would assume that there would be like around 10,000 optical photons. And we can measure those using Geiger-Müller counters. So this is a small piece of basically incorporating 50,000 Geiger-Müller counters. So it's the size is like 3 times 3 centimeters, but it is full of Geiger-Müller detectors. If you don't know what that is, usually they look like this. So there's like a gas, and if a radiation comes in, it triggers a chain reaction, and the whole chamber breaks through, and then you get once basically an information, I measured something. And if a lot of those Geiger-Müller counters are on this small piece of electronics, you can basically see how many of those triggered, for example, 9,000 of those triggered, and then you know, this might have been a gamma photon with 511 keV. You would never be sure that it was a 511 keV photon because there is something like detector resolution. So the number of triggered Geiger-Müller counters can be used to distinguish scattered and true coincidences to an extent. So, for example, this is a measured energy spectrum, and say in this case, after the particle hit, we measure 511 keV particle hit. We measure around, so this peak here amounts to the uncertainty we have when we measure 511 keV particle. So this whole peak here. However, as you can see, it is not always that we just measure 300 something, which corresponds here to the maximum peak. So it's not always like 320 photons we measure if one 511 keV gamma particle comes in, but we measure something with a certain width. And this is problematic because right here we can be sure that we have Compton scatter. There are just 100 particles, and that's like a factor of 3 less than what we would expect, like 320 or 340. So we know this is Compton scattering, but what actually is happening here? So let's say our peak looks something like this, and we measure most of the time 300 something, sometimes more, sometimes less, and the Compton scattering is looking something like this, then we don't actually know what is happening here. So it is not possible to upfront exclude all scatter coincidences from your measurement. Well, you could, but then you would have to set like a threshold here, and then you would reduce your sensitivity greatly because you would just measure half of the particles. So given that, it's not that easy to totally exclude them. As I said in another video, we will focus more on this. However, let's start with what actually happens once we measure those particles. How do we actually get the distribution of tracer in the patient? So this is the image reconstruction approach. And what it actually does, well, the problem is this here, this distribution in the patient is causing this measurement. So this is called an inverse problem because we want to go from the measurement back to the origin, to the cause of our measurement. So we want to find those positions. And what we usually do is, and now this is as complicated as it gets in this presentation. So usually, but I will break it down. So hopefully you'll get how we do it. So if you have a measurement, then we say, well, what would happen if our tracer was distributed in the patient like this? So even outside of the patient, which doesn't make that much sense. But let's say it's just homogeneously everywhere. Then we would measure something, and we know if this would be the case, how our detector would respond. So we can do a simulation, basically a very fast simulation, because we know, for example, the attenuation. So we can get basically a measurement how we would expect it to be. This is sometimes also called, if this is image space, then this is called projection space. And then we would say, well, do those two look similar? And in this case, they absolutely don't. They're just homogeneous here, and here they're all crossing in one point. So then we say, oh well, it was really, really different from what we expected. And then we can say, okay, along those lines of responses, there was way more. So we would expect it to be way more here. And then we can continue the process. We can go from here and go again to the forward model. We know now this was not a good estimate, but this is pretty good. And then we can go to the forward model, and now our expected measurement looks like something like this. And if those two are really similar, then we know this is a good, really good assumed distribution, which results in such a measurement. And this is, despite sounding really complicated, is giving you way less noise, and it is way better at handling scattered and random coincidences. And another fact I want to stress here, now we've done this basically one iteration, so we've done this once, this comparison, and at the second time we already said, oh well, this looks really similar. Usually you have to go through this way more often, so there are a lot of iterations. Let's say if you do something like 50 iterations or even more to 100 iterations, you might in the end end up with a model or a distribution that is really similar to the one you initially put in. And this distribution is our image in the end. So, and let's discuss again the image benefit. If we have this image and this image, so this was the CT, this was the PET, this image here is really crucial for deciding what treatment to do. So here you can see that there are metastases in certain regions, and you cannot see that from the CT. You can see here there's a higher uptake, you can see here's higher uptake, here's higher uptake, here's higher uptake. A lot of positions even here in the bone marrow. So this is crucial. On the other hand, there is a risk involved with PET imaging. So if you just assume linear non-threshold model of radiation risk, you would get to something like 0.08% chance that you develop fatal cancer due to performing the PET-CT. So that is because the PET scan and the CT both give you like 7 millisieverts, so basically deposit energy in your body, and this is a risk to develop cancer. And let's compare to some other, because those numbers are, yeah, I mean, this is a really small number, but what is actually compared to? So in Germany, the annual radiation exposure is like something like 4 millisievert. So there's 2 millisievert natural radiation and 2 from artificial sources, medicine, for example. And in some other places, for example, in Denver, and there are also some, there's a high natural radiation. And there are also places in Europe. And here you had like 12 millisievert natural radiation and again the 2 millisievert of artificial radiation you get. So living 1 year in Denver or getting a PET-CT scan amounts to the same risk approximately to developing fatal cancer. Let's still say there's still a risk. I mean, this number is incredibly low. It's 0.08%. But if you perform 140,000 scans, that means it's something like 11 patients actually develop fatal cancer due to the PET-CT, more or less. Obviously, you have to take into account that that there is still a benefit of these scans because you can choose the right treatment. And if you do the scans, you already have an indication for either cancer or it is something in neurology. So there is, in this case, a clear benefit in this case. In the end, the doctor has to say this has to decide this every time. There's always a risk involved in PET scan. And there's also a risk for others because you cannot switch off the radiation you get. So if you have, for example, FDG and a half-life of, well, it's around 2 hours, then you are still, even after 2 hours, emitting radioactivity. So there is a risk for others. It is again small, and in the end, well, you are for a large point in time you are basically quarantined. You're separated from everyone else, but there is a risk for others. And in the end, the question is this information more valuable than this risk? And while it sounds, yeah, I can believe that it sounds, yeah, scary to have radiation injected into you, but in the end, yeah, I think radiation, you do not need to fear it. It's nothing artificial that is destroying you, but you must have respect for it. In this case, it may help you more than it hurts you. And this information may be way more worth. All right, let's up. So in conclusion, PET, in general, PET imaging is based on different traces. And depending on the tracer, for example, sugar in oncology, estrogen in oncology, or PSMA, they all can show you different things in the body. And in all of the things, particle physics plays a major role, from the radioactive decay, the interactions of positrons, gamma particles, in the detector design, that all plays a major role in this medical imaging modality. And if you do it right, you get valuable information on the function of the tissue. And this can help you a lot detecting metastasis or displaying receptor status. And with that, I'd like to thank you. Thanks for listening. I hope it was interesting for you. And if it was, I have some other recommendations for you. So there will be other videos made by this group, Hybrid. I will do another video on understanding and distinguishing true, scattered, and random coincidences. And in this machine learning oriented talks, this will be basically image space reduction, so pre-processing in a way. And there will also be other videos on PET quality control and quantification, and a lot on machine learning in medical imaging. Yeah, if you want to know more, there's also our website, the Hybrid website, and you can actually look at those videos again. So they are also in the description. The links are down below. And if you have any questions, feel free to drop me an email. And with that, I say goodbye and have a nice day. Bye.